Hi there, welcome to problem 14 of the Problem Corner playlist. This is Soman and you're watching the Genesis YouTube channel. Today's problem involves a ring moving through a spatially non-uniform magnetic field. The problem goes like this. A very small conducting ring of mass m, radius a and resistance r is released from rest on an inclined plane of inclination theta with the horizontal. The plane of the ring lies in a vertical plane containing the line of steepest descent of the incline. A spatially non-uniform magnetic field B vector exists perpendicular to the plane of the ring, and the field depends on the x coordinate of the center of the ring as B vector is equal to minus 1 plus alpha x k cap, where alpha is a constant. The ring was released from a position where x is equal to 0 at t is equal to 0. Find the speed of the ring as a function of time. Neglect friction at all contacts. I suggest you pause the video and try to do it on your own. It's a beautiful question which is an exercise in both problem-solving discipline and lateral thinking. If you do it right, you can reduce calculations by a significant amount. Think carefully, plan well before diving into calculations. We now go ahead with the solution. The first thing that should strike you is that friction is negligible. Therefore, the ring slides on the incline. This rids us of any rotational motion aspect of the problem. Second, as the ring is moving through a non-uniform field, the flux of magnetic field through it is changing with time, and this induces an EMF in the ring. This induced EMF in turn drives a current in the ring. As parts of the ring are conductors carrying current in a magnetic field, they also experience forces. If you are unsure of the ideas that I have just mentioned, pause the video, open a textbook, read Magnetism to Electromagnetic Induction, and then come back. From here, you can take two approaches. We will go through them one by one and it will become clear which approach is better. The most common way in which students approach this problem is to try to find the magnetic force acting due to the current on the ring. This can be done quite easily. From Lenz's law, you should be able to show that the induced current I will be anti-clockwise. This I leave up to you to show. Pushing forward, to find the force on the ring, we take an element that subtends an angle d theta at the center of the ring and makes an angle theta with the x-axis. The force acting on the ring can be found from the relation df vector is equal to I dl vector cross b. For this, we note that the x-coordinate of the element is x plus a cos theta, so the field at its location will be b vector is equal to, now the relation for b vector was given in the question, instead of x just substitute x plus a cos theta. And the length element dl vector has a length ad theta. Using right hand thumb rule, you will be able to show that the force is radially inward. And as dl vector is perpendicular to b vector, the magnitude of force is just I dl into b. And this comes out as I ad theta into b at that location. Now, take an element which is the reflection of this element about the x-axis. You will find that the force has the same magnitude and points radially inward. Thus, for this pair, only the x component of the forces will add up, and the resultant will be dfr is equal to 2I ad theta b naught into 1 plus alpha times x plus a cos theta into cos theta. The cos theta is the component which is adding up, and this force will act in the negative x direction. Similarly, if we take mirror image elements about the y-axis, the fields at this location will be b vector is equal to minus b naught into 1 plus alpha times. Now these locations will be x minus a cos theta. The field only depends on the x coordinate, and both of these elements have the x coordinate x minus a cos theta. And the net force on them, as we have calculated before, the net force on them will be 2I ad theta b naught, and in the whole term everything remains the same. Only difference will be instead of x plus a cos theta, we will have x minus a cos theta. And note that this dfl force will be in the positive x direction. The net force on these four elements is thus df is equal to dfr minus dfl, and if I calculate this, this comes out 4ia square d theta alpha b naught cos square theta. And this net force comes along the negative x direction. So the net magnetic force on the ring is the integral of this from 0 to pi by 2. Notice that we had taken 4 elements in each of the quadrants, so the integration must only go to pi by 2, from 0 to pi by 2. This is a very simple integral which you can easily integrate. Integrating, you will be getting f is equal to I pi a square alpha b naught. Note that this expression for force contains current, and to find the current we need to use Faraday's law. To do so, we must know the flux, But as the magnetic field is non-uniform, that flux is not easy to calculate. However, remember the wording of the problem? The problem said a very small ring. Due to this, we can calculate the flux through the ring using the magnetic field at the center of the ring. Therefore, the flux will be B into pi a square, and since it's a small ring, we are assuming that the field is nearly uniform, and the approximate value of flux we get as B naught into 1 plus alpha x into pi a square. From Faraday's law, the magnitude of the current therefore is I is equal to 1 by R mod of d phi by dt, and that turns out to be B naught alpha pi a square by R dx by dt. Now what is dx by dt? Dx by dt is nothing but the x component of the velocity of the center of the ring. So if v is the instantaneous velocity of the center, then v cos theta is the x component, that is dx by dt is v cos theta, and substituting this in the current, we get the final expression for the current, which is B naught alpha pi a square v cos theta by R. And now if I substitute this into the expression for force, we get the value of the force as B naught square alpha square pi square a4 alpha v cos theta by R, which is acting along the negative x-axis. Now if we draw the free body diagram and include F in it, we can see that the equation of motion will become mg sin theta minus F cos theta is equal to ma. Substitute this value of F, this I am leaving up to you. Simplify, you will be able to show that you will get an equation like this: dv by dt is equal to g sin theta minus this huge term into v. Now this essentially is a differential equation of the form dv by dt is equal to a minus cv. You would have come across this equation many times in capacitor charging, in growth of current in an inductor, in Stokes' law, etc. The solution to this is extremely easy, and you should be able to show that the solution to this is given by v of t is a by c into 1 minus e power minus bt, where a here is g sin theta and c is this huge thing. Now, importantly, what we understand that this is essentially an exponential saturation with a terminal velocity vt, which is a by c, and that saturation goes with a time constant 1 by c. If you don't understand what is time constant or this concept of terminal velocity, I would suggest that you read through charging of capacitors and then come back, you'll understand this. This completes solution 1. At this point, I must mention to you that you can have avoided the force determination completely, and that is the crux of solution 2. The force calculation was not a very difficult one, but yes, it did take up some of our time. And the solution 2 will show us that how can we completely bypass the calculation of that force. So solution 2 goes like this. If we conserve mechanical energy for an elementary displacement, we can write work done by gravity is equal to change in kinetic energy plus heat dissipated by the resistance. And in dt time interval, the work done by gravity will be mg sin theta into the displacement along it, which is v dt, and change in kinetic energy mv into dv, this is a differential of half mv square, and heat dissipated by the resistance is I square r dt. Find the current as we have indicated. This was not very difficult to do by using the flux, and I am putting the expression for the current here. Now if I substitute this value of current into the energy equation, we get this expression. And now you can cancel off the m, you can make it into a differential equation of this form. And notice that this is exactly the differential equation that we got in solution 1. And from here, everything else is same. Integrate, you will find that this has a solution of the form a by c into 1 minus e power minus bt, where a is g sin theta and c is this huge thing. And it is very clear that in an examination, the second solution would save us time. In general, as a rule of thumb, you must apply mechanical energy, linear momentum and angular momentum approaches before you get on to the dynamics equations. This problem illustrates the importance of discipline and planning in any kind of problem solving. Again, tricks and shortcuts won't work here, and in any good problem, we must attack the problem from the basics and rely on our problem solving discipline to plow ahead. I hope you like this problem and its solution. Keep watching the Problem Corner playlist for more such unique problems and interesting solutions. JEE aspirants can also watch the solutions to JEE Advanced 2020 playlist. We also have a playlist called Essentials, in which we discuss problems that every physics problem solver must do. And finally, if you like the content, like, subscribe, and share widely amongst your friends. In the next video, stay safe and stay healthy, you all.